Hello all, hope you are doing well. In the last video, we have seen the important clauses related to the section 4, and in this video, we are going to see the important clauses in the section 5. So again, section 5 is made into two parts. This is the first part of the video. So let us start there. So basically, this section 5 is related to the clauses of limit state method. Okay, the section is related to the clauses of limit state method. Okay. If you have not watched any of our previous videos, the links were given in the description. You can watch them, then you can come back to this video. Okay, so let us start. Now, the first clause here is related to the crack width. Okay, first clause is related to the crack width. And you know that in the limit state method, there are two criteria. First one is the criteria of collapse, that is limit state of collapse, and second one is the serviceability criteria. Okay, there are two criteria for which we do the design. One is the collapse and second one is the serviceability. Now, as per this class, whenever you are designing, whenever you are designing a building, or else whenever you are designing a member, the crack width, the surface width of the crack, that means suppose this is the beam like this, and this is the bottom of the beam, and here a crack is generated, suppose. Okay, here on the surface a crack is generated. Internally whatever the cracks are there, that is unnecessary for us, but whatever the crack is there on the surface, its width should not exceed 0.3 mm. Okay, its width should not exceed 0.3 mm, and this should not exceed 0.3 mm where cracking is not harmful. Okay, where cracking is not harmful. So whatever the crack is there here, if it is not harmful to the member, then it can be 0.3 mm. And one more condition is, and does not have any adverse effect upon the preservation of reinforcing steel. That means whatever the 0.3 mm crack generated here, that should not show any effect on the reinforcement. Okay, so if the cracking is not harmful and if there is no problem to the reinforcement, then crack width can be maximum how much? 0.3 mm. So now this kind of exposure we can call like mild exposure. In the section 2 of this videos, I told you what is mild exposure. Suppose if the concrete is there, it is completely sheltered. Okay, the concrete is there, it is completely sheltered, and there is no aggressive condition. There is no concrete, doesn't have any contact with water, and concrete is sheltered, and there is no external exposure to the concrete. In such cases, we call as mild exposure. So if the concrete is sheltered, whether cracking will be harmful to the concrete? No. So in such case, what can be the maximum crack width? 0.3 mm. Then in members where cracking in the tensile zone is harmful. Okay, previously it was which is not harmful, but now it is harmful. Okay, harmful either because they are exposed to the effect of weather, are continuously exposed to moisture, or in contact with soil or groundwater. So if the concrete is there, suppose, okay, this is a member again, and here there is steel. Now a crack is generated here, and this member is continuously in contact with the water. Whether it will be harmful to the reinforcement or not? Yes. So in such a condition, crack width should not exceed 0.2 mm. Okay. So if it is not harmful to the reinforcement, then it is 0.3 mm. If it is harmful to the reinforcement, if the crack is harmful to the reinforcement or member, then it is 0.2 mm. Then for particularly aggressive environment such as the severe category. Okay, so first we have seen about the mild one, and this is about the moderate category. Okay, this is the moderate category. Okay, now in the severe condition, that means if the concrete is completely immersed in the seawater. Okay, the concrete is completely immersed in the seawater. In such a case, crack width should not exceed 0.1 mm. If the concrete is immersed in normal water, that is the moderate condition, their crack width should not exceed 0.2 mm. But if the concrete is immersed in the seawater, then it is highly dangerous. It is highly in the dangerous situation. So in that case, crack width should not exceed 0.1 mm. Okay, so remember these three things again. In the mild condition, crack width should not exceed 0.3 mm. For the moderate condition, crack width should not exceed 0.2 mm. And in the severe condition, crack width should not exceed 0.1 mm. Okay, then next class is related to the characteristic load. Okay, next class is related to the characteristic load. So what is this characteristic load is, suppose you are designing a structure. Okay, you are designing a structure which is of 3 floors, let us say, okay, which is of 3 floors. Now let us say life of the structure is 50 years. Okay, life of the structure is 50 years. Now, throughout the 50 years, okay, throughout the 50 years, whether the load will be same on the structure? No, it will not. Okay, the load will keep on varying. Suppose there are only 5 to 6 people are there in the structure, then load will be less. Suppose a flood is there. Okay, a flood is there, and people has to be mobilized to this building. Then they may mobilize up to 300 to 400 people. So in that case, loading will vary. But while designing a building for you, can you design it for the can you design it for 300 to 400 people? No, not possible, because if you want to design the structure for 300 to 400 people, the load will be heavy on the structure. Then size of the members increases, percentage of the reinforcement increases. Because of that, structure will not be economical. Okay, so we will not design for the case of 300 to 400 people. Okay, we will design it for the normal condition. Now what is characteristic load is, characteristic load is that value of load which has a 95% probability of not being exceeded during the life of the structure. So now suppose if you consider a load of 100 kilonewton, a load of 1000 kilonewton. Okay, you are considering that the load on the structure is 1000 kilonewton, then 95% of the times the load on the structure should be less than this 1000 kilonewton. 5% of the times, okay, less than 5% of the times it may exceed that value, but 95% of the times the load should be less than this value. Okay, so that is the characteristic load. So what is characteristic load? The load which has a 95% probability of not being exceeded during the life of the structure. Okay, so that's the thing. Next one is related to the factor of safety. Okay, next one is related to the factor of safety and the design strength of the material. Okay, design strength of the material. So now if you take the concrete, its strength is generally how much? FCK. Okay, if you take the concrete, its strength is generally FCK, and if you take the steel, its strength is generally Fi. But while designing a structure, you should not consider the full strength of the material. Okay, you should not consider the full strength of the material, because sometimes maybe it will have less strength than the required strength. Okay, that's why we have to consider some factor of safety. We have to divide with some factor of safety, and we have to calculate the design strength. Now if you are calculating the design strength of concrete, suppose if you are calculating the design strength of concrete, then it will be equal to grade of concrete divided by factor of safety of concrete, factor of safety for concrete. So what is that factor of safety for concrete in the limit state method is 1.5. Okay, it is 1.5. Then this partial factor of safety for the steel is, okay, if you take the steel, the design strength may be some FSD, the design strength may be FSD. This FSD equal to Fs by gamma ms, and whatever this gamma ms is there, that is the partial factor of safety for steel, and that is taken as how much? 1.15. So partial factor of safety for concrete should be taken as 1.5 and steel should be taken as 1.15. Okay, so if they ask you design strength, you have to divide with those two values. So next one is the design load. Okay, so this design load is given by Fd equal to F into gamma F. What is F here? F is the characteristic load. F is the characteristic load. So if you multiply this characteristic load with the partial factor of safety for the loads, okay, partial factor of safety for the loads, then you will get the design load. Okay, that means already you know the dead load and imposed load. Okay, already you know the dead load and imposed load. Okay, suppose dead load is 200 units, let us say. Okay, imposed load is 100 units and wind load is 150 units. Okay, like this they are. Okay, so now how to determine the design load? Okay, these three are the loads given, these three are the characteristic loads. Now I have to determine the design load. So how to determine that is, first check the combinations here. Totally there are three combinations, so you have to use all these three combinations. What is the first combination? Dead load plus imposed load, dead load plus imposed load combination. So now when you consider this, you have to multiply with the factor of safety of 1.5. So 1.5 into 200 plus 100. So that will be equal to how much? 450 units. Next you have to consider the dead load plus wind load combination. The dead load plus wind load combination. So dead load plus wind load combination, when you consider, again you have to multiply with 1.5. So 1.5 into 200 plus 150. So that is totally 350 here. 350 into 1.5, that is 525 units. In next combination, you have to consider all the three loads together. Okay, you have to consider all the three loads together. That is dead load plus imposed load plus wind load. Then how much it will be? Okay, then how much it will be? So that will be equal to 1.2 times of 200 plus 100 plus 150. So this will be equal to 540 units. Okay, this will be equal to 540 units. You don't need to worry about the limit state of service good here, because design load will be always higher for the collapse condition. Okay, design load will be always higher for the collapse condition because the factor of safeties are higher here. Okay, so here among these three, okay, among these three combinations, this is the first combination and this is the second combination and this is the third combination. So whichever is higher, that has to be used as the design load. That has to be used as the design load. Now you can see that a factor of 0.9 is given here. Okay, in the limit state of collapse, in the combination of dead load plus wind load, for the dead load, factor of safety of 0.9 is given. So if you remember, while discussing the clauses in the section 3, okay, while discussing the clauses in the section 3, I told that whenever the dead load acts as the resisting force, okay, whenever the dead load acts as the resisting force, it has to be multiplied with the 0.9. Okay, it has to be multiplied with the 0.9. So in that condition, you have to take like 0.9 into wind load, 0.9 into dead load plus 1.5 times of the wind load. Okay, 1.5 times of the wind load. Okay, so if the dead load acts as the resisting force, then you have to take like 0.9 here. If the dead load is not acting as the resistant force, then you have to take as a 1.5. Okay, that's why they have given two values here. The next class is related to the redistribution of moments. So this concept of redistribution of moment is related to the plastic analysis. It is related to the plastic analysis. Now, because of this redistribution of moments, advantage is the moments in the structure or else moment in the span reduces. Okay, moment in the span reduces. So remember that because of the redistribution of moment, moment in the span reduces, as well as moment carrying capacity of the structure increases. Okay, moment carrying capacity of the structure increases. Now here the first clause is the elastic moment at any section in a member due to a particular combination of loads shall not be reduced by more than 30% of the numerically largest moment given anywhere by the elastic maximum bending moment diagram. So let us see what is this class. So I am considering a continuous beam like this. I am considering a continuous beam like this which has 3 spans suppose. Now throughout the span we have applied the UDL like this. Okay, throughout the span we have applied the UDL like this. So now at the supports, at the end supports here, what will be the bending moment? It will be 0. Okay, here the bending moment is 0 and here the bending moment is 0. But at the interior supports, what will be the bending moment? It will be negative. Okay, at the interior supports, bending moment will be negative. Now at the middle span here, okay, at the middle span here, bending moment will be positive. So your bending moment diagram will be like this. Okay, now for the given structure, the bending moment diagram will be like this. So now here the maximum bending moment may be 100 kilonewton meter, here it may be 50 kilonewton meter, and here it may be some 45 kilonewton meter, and here bending moment may be 80 kilonewton meter, and here it is 70 kilonewton meter, and here it is 0. So like this the bending moment diagram is. Now what is numerically maximum elastic bending moment? That is 100 kilonewton meter. Okay, numerically maximum bending moment is 100 kilonewton meter. So now see this class again. The elastic moment at any section in a member due to particular combination of loads shall not be reduced by more than 30% of the numerically largest moment given anywhere by the elastic maximum moment diagrams. Okay, so now at no section, you take at any section, the moment values should not be reduced by. Okay, you take at any section, the elastic moment value should not be reduced by 30% of the numerically maximum bending moment. 30% of the numerically maximum bending moment. So here 30% of 100 means 30 kilonewton meter. So at no section you can reduce the given bending moment value by 30%. Okay, at no section you cannot reduce the given bending moment value by 30% of numerically highest value. So that means here if it is 80 kilonewton meter, by redistribution you can make it to 50 kilonewton meter, but you should not make it to less than 50 kilonewton meter. Similarly here it is 50 kilonewton meter, you can reduce it to maximum 20 kilonewton meter, but you cannot make a value less than that. Okay, so hope it is clear. Now hope it is clear. Again I am saying, whatever the elastic moment at any section is there, that can be reduced maximum by 30% of the numerically largest bending moment at anywhere. Okay, then next class, in the structures in which the structural frame provides the lateral stability. Okay, structural frame provides the lateral stability. Structural frame provides the lateral stability means structure is designed in such a way that it resists the wind loads. Okay, structure resists the wind loads. So if the structure is resisting wind loads, the frame is resisting what? Lateral stability. Okay, then structure provides the lateral stability. The reduction in moment allowed by condition 37.1.1c, that means this condition, shall be restricted to 10% for structures over 4 stories in height. Okay, so now if this structure has greater than or equal to 4 stories, suppose. Okay, the structure have greater than or equal to 4 stories. So in that case, the bending moment, the elastic bending moment cannot be reduced by more than 10%. Okay, so this clause is applicable. This clause is applicable only when the structural frame provides the lateral stability, and if the building is more than 4 stories in height. Otherwise, if it is less than 4 stories in height and if it is not providing the lateral stability, then you will take it as how much? You will take it as 30%. Okay, see the next class, clause number 38.1. These clauses are assumptions of limit state of flexure. Okay, assumptions of limit state of flexure. Okay, now the first assumption is plane sections normal to the axis remain plane after bending. Okay, plane section normal to the axis remains plane after bending. So what is this is, suppose consider a beam like this. You consider a beam like this. Now in the beam I am considering 2 sections which are like this. Okay, in the beam I am considering 2 sections which are like this. Now after bending, okay, after bending what happens is, after bending what happens is beam will come like this. Okay, beam will change like this. So now whatever the sections are there, they will be changing like this. Okay, whatever the sections are there, they will be changing like this. Now after changing, okay, so after, before bending they are straight like this. Now after bending also they will be straight in nature. Okay, there will be straight in nature. So because of this straight nature, okay, because these are straight in nature, we can say that strain variation is linear. Okay, strain variation is linear. So this clause is very important. This assumption is very important. Asked in many exams number of times. So what is this? Plane section normal to the axis remains plane after bending. That means strain variation is linear. Then next clause is the maximum strain. The next assumption is the maximum strain in concrete at the outermost compression fiber is taken as 0.0035. Now let us consider a simply supported beam like this, and this is the cross section of the beam. Suppose, okay, this is the cross section of the beam. So maybe bars are here. Okay, maybe bars are here. Then in this condition, if it is a simply supported beam, suppose, okay, if it is a simply supported beam, above the neutral axis fibers will be under compression, below the neutral axis fibers will be under the tension. So here at the extreme compression edge, okay, here at the extreme compression fiber, the maximum stress in concrete in bending will be 0.0035. Okay, remember that this is the strain diagram. Okay, so the maximum strain at the extreme fiber in compression will be how much? 0.0035. Okay, then area of stress block equal to 0.36 FCK into XU. Okay, area of stress block. What is that area of stress block is? In the limit state method, this is the area of stress block we consider. This is the stress block we consider. So now if you determine the area of the stress block, then it will be obtained as 0.36 FCK into XU. Okay, so what is the area of stress block? 0.36 FCK into XU. So why it is 0.36 FCK XU? If you want to know that, I have made another video on this, and that link was given in the description. You can watch that. Okay, but just remember now, for the sake of explanation, I am just saying that area of stress block is 0.36 FCK XU. Okay, so what is here? What is XU here? Is XU is the depth of the neutral axis. Okay, XU is the depth of the neutral axis from the extreme compression fiber. Okay, so suppose total depth, okay, total effective depth of the section is D, then XU is the depth of the neutral axis from the extreme compression fiber. Okay, so what is the area of the stress block here? 0.36 FCK into XU. Then next assumption is the tensile strength of the concrete is ignored. Okay, tensile strength of the concrete is ignored. So if you take the concrete which is in the tensile zone, it will also carry some tensile stresses. Okay, it will also carry some tensile stresses. But whatever the tensile strength of the concrete is there, that will be ignored, and total tensile stresses will be resisted by the steel only. The total tension will be resisted by the steel only. Okay, so whatever the tensile strength of concrete is there, that is ignored here. Next one, the maximum strain in the tension reinforcement in the section at failure shall not be less than Fi by 1.15 ES plus 0.002. Let us see what is that. So this is the stress strain curve of the steel. The stress strain curve of the steel this is. So now, in order to get the yield stress, okay, in order to get the yield stress, what we have done is, we have drawn an offset at the strain of 0.002. Okay, at the strain of 0.002, we have drawn an offset like this. Then, whatever the stress obtained at this point, that we have taken as the yield stress. Okay, whatever the stress obtained at this point, that we have taken as the yield stress. But for the design purpose, what we have done is, we have taken a factor of safety of 1.15. Okay, so our design stress is how much? Fi by 1.15. Okay, then what is the strain at this stress? Okay, what is the strain at this stress? What is the strain at this stress? Okay, so this is the strain. So now what is this strain? Okay, what is this strain? So up to this, the strain is how much? 0.002. Then what is this additional value is? Now here, whatever the slope of this line is there, okay, whatever the slope of this line is there, that is taken as what? ES. Okay, slope of this line is taken as ES. Okay, so here this strength by this slope, okay, this strength by this slope, that will give us the value of this. Okay, so what will be that value? Fi by 1.15 es. So what will be this total value now? 0.002 plus Fi by 1.15 es. Now what happens beyond this strain is steel starts yielding. Okay, what happens beyond this point is steel starts yielding. So if the steel starts yielding, what is the advantage to us? That will be a ductile failure. That means it gives us the warning before the failure. Okay, so you know that in the limit state method we always design the under reinforced section. So the purpose of designing the under reinforced section is to observe the failure, to observe the purpose of designing the under reinforced sections is to get the warning before the failure. Okay, to get the warning before the failure. So in order to get the warning, what should happen? Steel should start yielding. And when does that yielding happens? If the strain is greater than 0.002 plus Fi by 1.15 es. Okay, so see this class now. The maximum strain in the tension reinforcement in the section at failure, okay, in the section at failure shall not be less than this value, Fi by 1.15 es plus 0.002. Then only we will get which type of failure? Ductile failure. That means if this thing has to happen, we should always design which section? Under reinforced section. If the strain is less than this, and then if the failure comes, we can say that that is the over reinforced section, and the failure is of brittle failure. Okay, so this point is related to this note is related to the limiting values of depth of neutral axis. Okay, limiting values means nothing but XU max. Okay, XU max, or else you can call it as XU limit also. So what is this XU max or XU limit? Is balanced depth of neutral axis. Okay, balanced depth of neutral axis, or depth of neutral axis for a balanced section. Now what is balanced section is, so at the failure, if the concrete reaches its maximum strain, okay, at the failure if the concrete reaches the maximum strain, this is the strain diagram, and if the steel also reaches the yield strain, that is 0.002 plus 0.87 Fi by es. Okay, so if both the materials reaches these strains at the same time, then the type of failure is called as balanced failure. Okay, now in this condition, this is the XU max, and this total effective depth is small d. So whatever this XU max by d value is there, okay, whatever the XU max by d value is there, it depends on what? It depends only on the grade of steel. So for the grade of for the 250, okay, for the grade of Fe 250, it is 0.53, and for the grade of Fe 415, it is 0.48, and for the Fe 500, it is 0.46. So next classes are related to the compression members, and these are the assumptions we have to consider while designing the compression members. Okay, so first assumption is maximum compressive strain in concrete in axial compression is taken as 0.002. What is axial compression is, suppose this is a member, okay, this is a member, okay, or else instead of that, consider a column like this, and the loads are applied like this. So this column is now under axial compression. Okay, now if the load is concentric here, okay, the load is concentric here, throughout the section stresses will be same. Okay, throughout the section stresses will be same. That means here this is the cross section. Here at this point stress is P by A. At all the points stress will be what? P by A. So when the stress is same, obviously strain will be also same. Okay, so this is the stress diagram and this is the strain diagram. So now the point is, at all the points, okay, at all the points strain will be same, and that strain is 0.002. Okay, so in pure axial compression, maximum strain is how much? 0.002. Now if you consider a beam, suppose beam is subjected to bending. Okay, when you apply the loads like this, beam is subjected to bending and our stress strain diagram will be like this. So now in this condition, this is the neutral axis. So here strain at different points will be different. Okay, so under the bending compression, strain at different point will be different. That varies from neutral, that is 0 at the neutral axis, and at the extreme fiber the maximum value can be 0.0035. Whereas in case of the axial compression, the maximum strain can be how much? 0.002. That's the clause. Okay, so maximum compressive strain in concrete in axial compression is taken as 0.002. Then next clause is maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending. So now this is the case where the column is subjected to axial compression. But here in this case, column is subjected to both axial compression and bending. Okay, combined action. That means, suppose if the column is subjected to bending compression, okay, the column is subjected to pure bending compression, then here the strain may be 0 and here the strain may be 0.0035. If it is subjected to pure axial compression, throughout the section strain will be same, that is how much? 0.002. Now I am saying that column is subjected to both axial compression and bending. Okay, combined action of both axial compression and bending. Then in this case at this point, okay, in this case at this point, let us say strain is epsilon. Okay, let us say strain is epsilon. Then at this point, what will be the strain is 0.0035 minus 0.75 epsilon, minus 0.75 epsilon. So here it is the least compressed fiber and it is the highly compressed fiber. Okay, it is the least compressed fiber and it is the highly compressed fiber. Okay, so see the clause again, maximum compressive strain at the highly compressed extreme fiber. Okay, so this is the highly compressed extreme fiber. So at this point maximum strain is, when the maximum strain shall be 0.0035 minus 0.75 times the strain at the least compressed extreme fiber. 0.0035 minus 0.75 times the strain at the least compressed extreme fiber. So that is what you have taken here. So at the least compression fiber strain is epsilon. So at this point strain is 0.0035 minus 0.75 epsilon. So these are the two assumptions of the we have to consider while designing the axial compression members. So these are some of the important clauses in section 5, and the remaining clauses of section 5 we will see in the next video. If you like our video, please share it to your friends, and you can subscribe to our YouTube and Telegram channel. The links were given in the description. Thank you. Hello all, hope you are doing well. In the last video, we have seen some of the important clauses in the section 5, and the remaining clauses we will see in this video. If you have not watched that video, link was given in the description. First you can watch that, then you can come back to this video. So let us start it. So these clauses are related to the design of axial columns. Okay, the clause is related to the design of axial columns. So what is this clause is, when the minimum eccentricity, that is E minimum, does not exceed 0.05 times the lateral dimension. Okay, so when you take the E minimum, if it does not exceed 0.05 times of lateral dimension. So lateral dimension means, suppose this is the column section. Okay, column section, this may be taken as a D and this may be taken as a B. So these two are the lateral dimensions here. So if the E minimum in both the directions, if not exceed 0.05 times of lateral dimension, then column can be designed using this equation. The column can be designed using this equation. So what is this equation? Pu equal to 0.4 FCK into AC. What is AC? Is area of concrete, plus 0.67 Fi into ASC. What is ASC? Is area of steel in compression. Okay, area of steel in compression. Okay, so if you use this formula, then you will get what is the design load. Okay, what is the design load the column can carry. Okay, then whatever the E minimum is there, that has to be determined using the clause number 25.4 of section 3. So what is this E minimum is L by 500, that is the unsupported length of column, plus dr b by 30. Okay, d by b are 30, or 20 mm, whichever is higher. Okay, whichever is higher you have to take. Okay, so higher among these two values has to be taken as the minimum eccentricity, and if that minimum eccentricity is not exceeding 0.05 times of lateral dimension, then only we can design the column using this equation. Suppose if it is exceeding that condition, okay, if it is exceeding, if the E minimum is exceeding this condition, then column has to be designed considering the bending. Column has to be considered designed using the bending. So in that case it may be column with uniaxial bending or else column with biaxial bending. Okay, so in such cases you have to design the column using the SP16 charts. Okay, you have to design the column using the SP16 charts. Okay, next class is related to the helical reinforcement. Okay, next class is related to helical reinforcement. So what is this class is? What is this first class is? The strength of compression member with helical reinforcement. Okay, strength of compression member with helical reinforcement. That means you have designed a column using the helical reinforcement. Then its strength will be equal to 1.05 times of strength of column with lateral ties. Okay, strength of column with lateral ties. Lateral ties means simply we tie the bars like this. Whereas in the helical reinforcement, we will provide the reinforcement like helicals like this. Okay, so now whenever you are providing the helical reinforcement, then strength of the column has to be increased by how much percentage? 5%. So the factor will be how much? 1.05. Okay, now in order to apply this condition, that is 1.05 times of the strength of similar member with lateral ties, it has to satisfy a requirement here. Okay, it has to satisfy a requirement. So what is that requirement is the ratio of volume of helical reinforcement. Okay, let us say it is VH. Okay, ratio of volume of helical reinforcement to the volume of the core. Let us say volume of the core is VC. So that ratio VH by VC, that shall not be less than, okay, that shall not be less than 0.36 times of AC by AC minus 1 into FCK by F5. So let us see what is this VH VC. So first, if you take the column diameter like this, okay, if you take the column diameter like this, then you can determine the gross area of the column, which is AZ. Okay, so what is AZ is gross area of the column. So that will be equal to how much? Pi by 4 into diameter square. Then what is this? Whatever this area is there. Okay, whatever this area is there, I mean whatever this diameter is there, suppose this is small d, then this portion, okay, this inner circular portion, whatever you can see here with dotted lines, that is called as core. Okay, so here this is called as area of core, and what will be the formula for that? Pi by 4 small d square. Then you have another two terms, VH and VC. Okay, VC means nothing but volume of core. So simply this pi by 4 into d square into, let us say, height of the column is h. The height of the column is h. So pi by 4 into d square into h, that will give us the volume of the core. Then what is VH is? It is volume of the helical reinforcement. Okay, VH is the volume of the helical reinforcement. So now whatever the helix you can see here, okay, whatever the reinforcement you can see in the helical form, if you determine the volume of that, that will be the VH. Okay, so now if you substitute all these things here, and if this condition is satisfied, then only we have to take 1.05 times of the strength of similar member. Otherwise, what we have to take directly, we have to take PU value only. Okay, that's the point. Next one, nominal shear stress. Okay, so basically, if you take a RCC beam like this, if you take an RCC beam like this, let us say this is the singly reinforced beam, then actual shear stress distribution will be like this. Actual shear stress distribution will be like this. That means up to neutral axis. Okay, up to neutral axis, the distribution will be parabolic in nature. Okay, this is what actual shear distribution. And below the neutral axis, okay, below the neutral axis, it will be rectangular in nature. Now the thing is, if you take this distribution, then analysis will become difficult. Okay, analysis will become difficult. That's why what IS code is saying, that IS code is suggesting nominal shear stress which will be uniform throughout. Okay, which will be uniform throughout. And for that nominal shear stress, the formula is tau V equal to VU by BD. Okay, tau V equal to VU by BD. So what is this VU is? VU is shear force at the section. Okay, so shear force at the section divided by effective area. That will give us the nominal shear stress directly. So remember that nominal shear stress is constant throughout the depth, whereas actual shear stress is parabolic up to neutral axis, and below that it is rectangular in nature. In the case of beams of varying depth, the equation shall be modified as. Okay, so now sometimes what happens is, beam will not have a longitudinal section like this. Okay, instead beam will be like this. You see the longitudinal section of the beam, it may be like this. So what happens here is depth of the beam. Okay, depth of the beam is increasing in this direction. Okay, depth of the beam is increasing in this direction. Of course, after the central point, again it is decreasing. Now the thing is, whenever the depth of the beam is varying, then you have to calculate the nominal shear stress using this formula here. So what is that formula? Tau V equal to VU plus or minus mu by d into tan beta divided by BD. So what is VU and mu are? VU and mu are shear and bending moment at that section. Okay, then what is beta here is, suppose this is the cross sectional and this is the column, this is the longitudinal section, then determine the angle here. Okay, see, determine this angle here. This will become the beta. Okay, then in the equation you can see a symbol here, that is plus or minus signs. That means sometimes you need to use the plus sign and sometimes you need to use the negative sign. So how to use that is, suppose in this direction, okay, in this direction up to this point, okay, up to the central point I am taking, in this direction up to the central point, what is happening to the depth? Depth of the beam is increasing. The depth of the beam is increasing. Then what happens to the bending moment in this direction? Okay, bending moment in this direction increases. So now if both depth and bending moment increases in this direction, you have to use the plus sign. Okay, you have to use the negative sign. Okay, suppose one of the parameter is increasing and another parameter is decreasing, then we have to use the positive sign. Okay, so remember that if both these parameters increases in the same direction, you have to use the negative sign. If one of them increases and another one of them decreases, then you have to use the positive sign. Okay, so using this, you have to calculate the nominal shear stress whenever the depth of the beam is varying. Okay, next class is comparing the tau V and tau C max values. Okay, tau V and tau C max values. So basically this tau C max value, it is taken from the table number 20 and it is constant for given grade of concrete. Okay, for given grade of concrete, it is constant. So remember that tau C max value depends only on what grade of concrete. Then whatever the tau V value is there, already we know how to calculate that using the formula of VU by BD, or else using the formula of VU plus mu by d into tan beta divided by BD. So using those formulas you can calculate the tau V value. Now this clause says that in no case tau V can be greater than tau c max. Okay, in no case tau b can be greater than tau c max. So if tau b is greater than tau c max, okay, then what we have to do is we have to redesign the section. Okay, so in no circumstance tau b can be greater than tau c max. That's what this class is regarding the shear reinforcement. Okay. So when we have to provide the shear reinforcement is, when we have to design the shear reinforcement is when tau b is greater than tau c. Okay, when the tau b is greater than tau c. What is tau b? Tau b is the nominal shear stress. Then what is tau c is? Tau c is the shear strength of the concrete, shear strength of section without shear reinforcement. Okay, without shear reinforcement. That means even if you are not providing the shear reinforcement, because of the presence of concrete and because of the presence of main reinforcement, the section will have some shear strength. The section will have some shear strength. Now, when the tau b is greater than tau c, that means whatever the shear resistance offered by the section without reinforcement is not sufficient. Okay, not sufficient. So in that case, what we have to do is we have to provide the shear reinforcement. We have to provide the shear reinforcement. Then that shear reinforcement is provided in three forms: vertical stirrups, bent up bars along with the stirrups, and inclined stirrups. Okay, you can provide the shear reinforcement in three forms. One is the vertical stirrups, the second one is bent up bars along with the stirrups. That means you cannot provide the bent up bars alone, you have to provide the bent up bars along with the combination of the stirrups. Then you can provide also inclined stirrups. Then whatever the shear reinforcement you are providing, that shall be provided to carry a shear force of VUS equal to VU minus tau CBD. The actual shear force at the section is VU, but already without the reinforcement it is having some shear strength. So that shear strength into area, effective area, that will give us the shear force that can be resisted by the section without reinforcement. Now, whatever the tau c value is there, it is taken from the table number 19. Okay, tau c is taken from the table number 19. So now this tau c value depends on two parameters. Okay, tau c value depends on two parameters. First one is grade of concrete. Okay, tau c depends on the grade of concrete, and second one is it depends on the area of the steel. Okay, area of the tensile steel. Okay, so remember that tau c depends on two parameters. First one is the grade of concrete, and second one is area of tensile reinforcement. Then if you take tau c max, that depends on which parameter. Tau c max depends on only grade of concrete. Okay, that's the thing. So I told that shear reinforcement has to be designed for the shear force of VUS. Okay, shear reinforcement is designed for the shear force of VUS. Now we have told that we can design the shear reinforcement either in the form of vertical stirrups, inclined stirrups, or bent up bars. Suppose if you are using the vertical stirrups, then already you would have fixed what is the grade of the steel you have to use. Okay, already you would have fixed what is the grade of the steel used. Now remember that in no case Fi can be taken as greater than 450 Newton per mm square here. Okay, so whatever the Fi value is there, that can be maximum 450 Newton per mm square. Suppose if you are using Fe 500, okay, if you are using Fe 500 still you have to take that Fi like 415 Newton per mm square only. Then already we have designed the section, so we know the effective depth of section, and we already know what is the shear force for which we have to design the shear reinforcement. That means we have seen how to calculate this VUS. What is VUS? VU minus tau c into BD. Okay, so like that we have calculated VUS. Now what are the remaining things here? ASV and SV. ASV and SV. So now what is ASV is, suppose there are 4 bars like this. Okay, there are 4 bars like this, and you are providing the stirrup like this. Okay, there are 4 main bars. This is the main reinforcement. So there are 4 main bars and you are providing the stirrups like this. Then ASV will be equal to 2 into pi by 4 into diameter square, because the two legs are there. Okay, two legs are there. So you can see that here. Suppose this is a longitudinal section of the beam. Here there is a stirrup. Now, whatever the crack generates here, okay, whatever the crack generates here, it has to cut the stirrup at the two places like this. Okay, that's why you have to take like ASV equal to 2 into, and here the area is pi by 4 into diameter square, here the area is pi by 4 into diameter square. That's why I am taking it as 2 into pi by 4 into 2 into pi by 4 into phi square. Suppose you have provided the stirrups like this. Okay, you are providing the stirrup like this, something like this. Let us say that means this is which stirrup? Three-legged stirrup. So in this case, what will be ASV? 3 into pi by 4 into phi square. So how to calculate this ASV is number of stirrups legs into pi by 4 into diameter of the stirrup square. Okay, like that we have to calculate the ASV. So now once if you know this ASV also, what you can determine? You can determine spacing between the stirrups. Okay, you can determine the spacing between the stirrups. So that can be calculated using this equation. Now this is valid for the vertical stirrups. Suppose if you are providing the inclined stirrups, okay, if you are providing the inclined stirrups, you have to multiply the same equation with sin alpha plus cos alpha. Now if you compare vertical stirrups and inclined stirrups, which offers more resistance? Which offers more resistance? You can say that from the equation. So inclined stirrups offers more resistance than the vertical stirrups. What is the reason is, here you can see the sin alpha plus cos alpha, which will be always greater than or equal to 1. Okay, sin alpha plus cos alpha is always greater than or equal to 1. So you can say like inclined stirrup offers more resistance. Then if you are providing the bent up bars, suppose, okay, if you are providing the bent up bars, it will be 0.87 Fy into ASV into sin alpha. So what is alpha here is either here or here, that is the inclination of stirrup. Okay, inclination of stirrup. Or else if you are providing a bent up bar, suppose this is the beam longitudinal section and you are providing the bent up bar like this. Okay, then this will become the alpha value here. Okay, this will become the alpha value. Okay, so like that you have to design the shear reinforcement using these equations. So this next clause is regarding the torsion. The next clause is regarding the torsion. So here the clause is sections located less than a distance d from the face of the support. From the face of the support. Suppose this is the beam now again, and this is the face of the support. This is the face of the support. This is the face of the support. Now whatever the sections located at a distance less than small d. Okay, whatever the sections located at a distance less than small d from the face of the support may be designed for same torsion as computed at a distance of d. Okay, so now the point is critical section for the torsion will be at a distance of d from the face of the support. Okay, so here the shear may be higher, but that should not be considered while designing. So where you have to consider the critical section at a distance of d from the face of the support. That is the point. Okay, then actually speaking, you cannot provide the reinforcement directly for the torsion here. Okay, you cannot provide the reinforcement directly to resist the torsion, because whatever the torsion is there, it will cause twisting in the beam. Okay, whatever the torsion is there, it will cause a twisting of it. So now if in order to resist the twisting, you have to provide the reinforcement in form of the spirals. Okay, in order to resist the torsion, in order to resist the twisting, you have to provide the reinforcement in the form of the spirals. But as the beams are rectangular in section, can you provide the reinforcement in the form of spirals? Not possible. So that's why what we have to do is we have to provide the torsional reinforcement in two forms. One is the longitudinal reinforcement, another one is the shear reinforcement. Okay, so torsional reinforcement is provided in two forms. One is the longitudinal reinforcement, another one is the shear reinforcement, that is the transverse reinforcement. Now, in order to provide that shear reinforcement, we have to calculate the equivalent shear. Okay, we have to calculate the equivalent shear. So, what is this equivalent shear? Is equivalent shear equal to VU. VU means already we know that is the shear calculated at the critical section. So that shear calculated the critical section plus 1.6 into TU. TU means nothing but a torsional moment. Torsional moment divided by B. So this gives you the equivalent shear. Now while designing the shear reinforcement, what we have to do is we have to design it for the equivalent shear. Okay, we have to design it for the equivalent shear. If you are not considering torsion, shear reinforcement is directly designed for the VU. If you are considering torsion, you have to design the shear reinforcement for the V equivalent. So what is the formula for the V equivalent? VU plus 1.6 TU by B. Very, very important formula. Okay. Then whatever the longitudinal reinforcement is there, that shall be designed to resist an equivalent bending MEQ equal to MU plus MT. So MU is the bending moment due to the applied loads and MT is additional moment due to the torsion. Additional moment due to torsion. So what is this MT? That is given here. So what is MT? TU into 1 plus D by B by 1.7. Okay, so MT is TU by 1.7 into 1 plus D by B. What is capital D here? Capital D is the total depth of the section. So now the thing is, whatever the longitudinal reinforcement is there, that has to be designed for M equivalent. If you are not considering torsion, you have to design it for MU, but if you are considering torsion, you have to design it for M equivalent. Okay, so that's the thing. So both these formulas of V and MEQ are very, very important. It was given in a number of competitive exams different times. Okay, so this is about the section 5 of the IS 456-2000. Hope you enjoyed this video. In the next video, we are going to see what are the annexures. Okay, what are the annexures available in the IS 456-2000? So the first annexure is regarding the working stress method. Okay, first annexure is regarding the working stress method. That we will see in the next video. If you like the video, please share it to your friends and please subscribe to our YouTube and Telegram channel. The link was given in the description. Thank you.